Hello friends, welcome back to Scientific Blunders where you learn the don'ts first. So today we're going to start a new series on series and progression. And if you're wondering why I'm starting this all of a sudden, it's because I was reading a book called The Man Who Knew Infinity, which is a biography on the great South Indian mathematician Srinivasa Ramanujan. And I was really inspired by how someone with no formal mathematical training could just achieve so much in a short lifespan of 30 something years. And so, as a tribute to the great mathematician, um, I thought we should start a series on what I think is one of his favorite and his area of expertise, which is infinite series. Although the problems that we are going to do are much simpler, but going to be very interesting nonetheless. So let's get started. So let me scroll down to make some space, and here's the problem. We want to evaluate the sum of 1 by x, where x starts from 1, then goes to 2, 3, all the way to infinity. So all of the natural numbers. And this is known as the harmonic series, right? And we just have some other series just for reference, okay? So here's the geometric series, half plus 1/4 plus 1/8, all the way to infinity. That magically sums up to 1. So even though you have infinite terms, they get smaller and smaller. So it converges to 1. Then you have the what is known as an AGP, an arithmetico-geometric progression. So you have half plus 2 by 4th plus 3 by 8th plus 4 by 16th plus 5 by 32 and all the way to infinity. That converges to 2. Okay, and so again you see the terms are getting smaller and smaller, but since they are so small, the series ends up converging to a finite value. And now the final series that we have for reference here is a famous one known as the Bessel's problem. So this is 1 plus 1/4 plus 1/9 plus 1/16 all the way to infinity. And this magically sums up to pi squared by 6. So pi is usually associated with a circle, but when you sum these numbers up, magically you end up with a pi squared by 6. And this is a topic for another video. But the point is, the general trend we are observing here is that as these terms, as you sum up infinite terms, with the terms getting smaller and smaller, typically it converges to a number, to a finite number, right? It converges, right? So similarly, we are summing up, what are we summing up in this series? So let's call that S first, okay? So we are summing up 1 over 1, which is let's see, I want to do this properly. So we are summing 1 over 1, correct, which is 1, and then we are adding to that. If you're wondering why I'm taking the pain to do this in separate colors, I hope that becomes clear in a second. And then we are adding 1/2 to that, correct, and to that we are summing 1/3, and then to that we are adding 1/4, and so on. So let me choose a different color for that. Okay, then we have 1/4 and so on. So this goes on and on. I just lost that blue color. Okay, there we go. And if you're wondering why I'm doing this in different colors, that should become clear in a second. So this is the series we want to sum, right? So it's 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 all the way to infinity. And having seen these three series, it's natural to think that this should also converge to some number, right? And I am not aware of any formula to like sum this to n terms and then take the limit of n tending to infinity. But in these cases, I have actually learned a very neat trick to be able to establish a lower bound. Okay, and what do I mean by that? So let me construct a graph first. Okay, so right here we are summing up 1 over x, right? So let's say, so the x-axis is x, The y-axis is y equals 1 over x. So what does that look like? So that's going to be, I should do a better job with that. Let's actually, yeah, I think this is probably the easiest way to draw a neat plot. So it's going to fall like this. Okay, so let's scroll down to create some space. Okay, and so we want to sum up this series, right? So instead of just treating it as a sum of numbers, whoa, sorry about that. Okay, I like to treat it as a series of, I like to think of it in a more geometric sense. Okay, and what do I mean by that? So when x equals 1, y equals 1, correct? When x equals 2, what does y equal? Y equals 1 half. When x equals 3, what does y equal? Y equals 1/3. 1/3. Okay, that is, that is because we are plotting 1 over x, as simple as that. Now what exactly is this 1? Can we have a more geometric interpretation for that? Well, yes. So 1, let's consider this rectangle here. Okay, so if you look at the area of this rectangle, the height is 1 and the width is 1, right? So this 1 is nothing but the 1 here. And what is half? Well, let's consider the next rectangle. Okay, over here, and this has a height of 1 by 2 and a width of 1. So this has an area of 1 half, correct? And that is nothing but this term here. And I think you might already see where this is going. Okay, but let's consider one more term here, and this is going to be really tiny. I don't think I'll have space, but this has a y value of 1 over 4, right? Okay, anyway, the third rectangle is going to have a height of, so it's right here, it's going to have a height of 1/3 and a width of 1. So this is going to have an area of 1/3, and so on and so forth, right? So just for completeness, I am going to draw the fifth or the fourth rectangle. Okay, and that is going to be have a height of 1/4 and the width of 1, right? So this is going to look something like this. So the point is, this, what just looked like a sum of numbers is actually a sum of areas of rectangles. So 1 corresponds to that area, 2 corresponds to that, 3 corresponds to that, and 4 should do this neatly. 4 corresponds to this. So what I'm actually doing when I'm summing this series is summing up the areas of these rectangles. Okay, and like I said, I don't think there is like a expression to sum this to n terms. Okay, but what we can say for sure is that the sum of the areas of these rectangles will be greater than the area under the curve. So how do I say that? If we notice this, see, the rectangles all pass through this point on the curve, right? So each rectangle exists entirely above the curve in a particular interval. So from 1 to 2, this rectangle, entirely covers the curve, and it has a little area above that, right? So if we sum up the areas of all of these rectangles, it will be greater than the area under the curve, right? So using that, we can establish a lower bound for this sum. So S will be greater than the area under the curve, and since we are summing this to infinity, we want to take the area under the curve from 1 all the way to infinity, correct? So the sum will be greater than the integral of 1 to infinity of 1 over x dx. I hope you understand this. We are establishing a lower bound for the sum because the area of the rectangles, some of the areas of the rectangles will be greater than the area under the curve. Okay, and this is very easily evaluatable, right? So let's integral 1 over x dx from 1 to infinity. So this is the beauty. A sum was very hard to do, but an integral is very easy. So we can use an integral to establish a lower bound for the sum. And integral 1 over x dx is log x, and going from 1 to infinity. So log infinity is infinity, log 1 is 0. So this equals infinity or tends to infinity, right? And now here's the crux of the video. If this thing tends to infinity and something is greater than that, okay, that means S must also tend to infinity. Right? And let's try to understand this. S was the sum of the harmonic series, right, that we started with. So the beautiful thing is, even though all of these other series, had the same trend, so you get smaller and smaller but you converge to a number, the harmonic series is unique because even though you get smaller and smaller, it tends to infinity. And we have just proved this in a very interesting way, where we establish a lower bound for the sum by observing that the sum of the areas of the rectangles will be greater than the area under the curve, right? And so I think the key lesson to be learned from this video is that any series that where you start off with a number and you get smaller and smaller, so all series do not converge. So just because it starts with a number and you get smaller and smaller and smaller, you may not always converge. And a great way to do that is just the technique that I just showed you. So think of the sum as the sum of the areas of rectangles and try to compute the integral. And it should be greater than that. If the integral itself tends to infinity, then your sum will diverge. But if the integral is a finite number, then your sum may or may not diverge, right? And so I hope you found this video useful. And the key takeaway is that all infinite series do not converge. Thank you.